And old homeworks are up here. You've got another one due Monday, right? I'll try to get you another one Monday, and then we'll make it due that same week. And hopefully I'll get you a third one before the exam. Okay. So yeah. Okay, we've got a lot to cover today, so let's dive right in. So what we're going to do today is to derive some equations that describe this. Rather than just drawing it graphically, we're going to start to be able to calculate them via math. And we're going to do that for a bulk system, then we're going to do that for increasingly smaller nanoscale systems, okay? And so at the end of the day, you're going to have equations for these three these you already know how to do this, but the density of states and essentially the number of carriers for 4 different systems, right? The 4 different systems are bulk, 2D confined, 1D confined, 0D confined. And if that doesn't make sense, it hopefully should soon. Okay, so the first thing we need to just be sure that we understand is what do we mean by K-space? And so I talked about it briefly, but what if we are trying to convert something from the time domain to the frequency domain, okay? So if we had a sine wave that looked like this, that has an amplitude A. Now if we just plotted this similarly, where this is A, we could plot this as a frequency, right? And it would look like that. There's one frequency there, right? Now if we added this, amplitude's the same, frequency's higher. So this would look like this, right? And this is probably not exactly right, but higher frequency, same amplitude, right? And then if we had something like in between, okay, so lower amplitude, maybe 1/2 A, and a frequency that's somewhere in between, it would look like that. Neat, right? It's a whole different way of thinking about these kinds of science. So frequency domain, time domain. So this is another way of showing it, right? Where you can look at our time domain signals, but if our time domain is a sum of all of these different frequencies, then they're going to, it makes sense that it's going to be additive, right? So if you look at this peak here, it's trying to convince you that that peak overlaps with that peak, overlaps with that peak, so it's additive, right? So if you look at in the time domain, you can't discriminate any of the frequencies, but you can in the frequency domain, okay? Good. So this, yeah.
Wait, so is that a graph of frequency versus amplitude?
Yeah. Yep, we're plotting. Well, I wouldn't think of it as a function of. I would think of it as it's ish, a Fourier transform ish. Yeah. Yeah. But to think of it as a function, I don't think is entirely accurate.
So then how exactly do you go through the left hand to the right hand?
So this is just kind of, mathematically?
Or like, even just like...
Okay, well, does this make sense that the white one, just start with the white one, it has some frequency that's short, right? And the amplitude matches the amplitude, right? This blue has a higher frequency, right? Zoop, but higher, so higher frequency, but same amplitude, right? Red has a frequency that's somewhere in between and an amplitude that's lower. Okay? So the point is that you can use this concept of frequency, and in this frequency domain and time domain can be moved back and forth by something called the Fourier Transform. And this was named after French mathematician Fourier. And the frequency domain is also lovingly referred to as K space. Okay? So this is an incredibly powerful technique, right? Do you guys know how MRI works? MRI works by you put your thing in a magnet and you hold it at a magnetic field, and then you pulse the magnetic field and you look at the frequency of all of those protons relaxing back to ground state, right? So if you were imagined that you had all of the protons in your brain emitting frequencies at the same time, what would this possibly look like, right? If you have how many protons are in your brain and they're all relaxing with these different frequencies. So it would be this huge mess, right? And so what MRI does is does an inverse Fourier transform. This is the raw data that comes out of the MRI instrument. You do an inverse Fourier transform and then it looks like a skull. Isn't that amazing? Yeah. So this is obviously a multi-dimensional kind of representation of this that we just don't have time to get into. But if you, who's used ImageJ? ImageJ is a piece of freeware that it's a very employable skill, image processing, and rather than using, it's always free no matter where you go. So I just wanted to, for fun, just quickly show what this is. I'm working on my Bolivian visa to go to Bolivia this Christmas. And so this is the Fourier transform of this image. Okay. One thing I didn't mention is, let's say then you start to have a compilation of many different frequencies, right? Let's say you have a signal that starts to look like this, right? What would the frequency domain of that would look like? Essentially a sum of these individual frequencies, right? There's one here that's kind of dominating, right? Like that one is by far the primary contributor to this messy signal. So that is this one. But then there's other stuff going on here, and that's these smaller amplitude other frequencies. Okay? So that is kind of what this is. What this does in less than a second is it transforms this image into a series of frequencies, right? So what's kind of cool then is then you can start to cut out these different areas. So I just went into the Fourier transform of my image and deleted a lot of this data, okay? This is what it looks like. I don't really make any difference. And the reason is because this spot here, the biggest contributor, is right in the center, okay? So these are essentially polar coordinates, and then at each pixel here is a frequency. But I've retained the frequencies that are the biggest contributors to that image. Yeah?
So how do the pixels capture the color image?
I gotta skip that one, yeah. Yep.
So is the frequencies in this case are like the different, like, are the different colors like that are making up the image, or what are the?
Every pixel in here has a polar coordinate, a frequency, and an amplitude. Okay? Every pixel in here does. Okay? Yeah.
So if there's like no frequency at a certain point, would that just come out as white or black?
Black. Yep. Yep. Bye.
You said that the biggest contributor is in the middle of the graph, right?
That's right.
Does that mean that it's also in the middle of the
Nope,
picture?
absolutely not. No, because in the graph is these pixels here have nothing to do with the pixels over there, because those are Cartesian pixels and these are polar pixels. Yeah.
So were pixels redefined in the Fourier transform picture?
Yes. Yeah.
And is it like a standard for all pictures? So if you look at a certain pixel, that is a certain amplitude and frequency of something being emitted, and then in every picture, if there's that same amplitude, that's what it is.
Every pixel has a pattern that looks similar to this because there are certain, for example, there's a frequency about the shape of the image, right? There's a frequency to the intensity of the different pixels. Yeah. Really, we can't burn a lot of time on this. But I just wanted to show you the power of this technique. Now, what if I went in and deleted this very tiny area in the center and back transformed it? Now, that's what I get, right? Because I've diluted. Who knows principal component analysis? You can kind of think of this, okay. What I did is I eliminated the most important contributors to that image, okay? And so similarly, I can delete these giant things, and it's a little blurrier, but then I could delete these areas that are much closer, and I gave myself a double chin, right? So this is you could take a whole class on the Fourier transform, but I just wanted to do this to let you start to think about how frequencies, a summation of frequencies can lead to a plot. Yes?
Taking it back to frequency, K is what we call the wave number, right?
That's right, yes, thank you. K is the wave number. And so then if we are in a situation where we have a semiconductor, and we have this three-dimensional semiconductor, and the wave function of all of the component atoms have overlapped, okay? So therefore, we're going to have frequencies in the K, X, Y, and Z. What's the convention on this? K, X, Y, and Z. Yeah, I was doing it right. Does that make sense? That we could plot frequency like this. This is Kx, Ky, and Kz, because we have the summation of these wave numbers in these different dimensions, because we have a three-dimensional semiconductor. Okay? Let's go back to some of our other assumptions. That the density of states in a semiconductor is the density per unit volume and energy of the number of solutions to the Schrödinger's equation. We discussed that previously. That the semiconductor for this derivation we're going to model as an infinite quantum well with electrons mass that can move. The energy in the well is set to 0. The energy on the edges is 0, right? Kind of like we did for a particle in a box, okay? Although we kind of rushed through particle in a box. We're going to assume that this semiconductor is a cube with side L, okay? And this assumption does not affect the density of states, because density of states by definition is per unit volume, okay? So whatever we're using here for this shape is kind of irrelevant, okay? These were good resources that if you want to go back and look at these for more of the derivation, I found to be helpful. Okay, so there's two places where we've just got to do some hand waving because we didn't have enough time to get through all of the quantum. The first one is this one, where the wave function in this semiconductor is going to be a summation of constant A times the sine of that wave number sub x of x, and b cosine wave number x at x, okay? Same thing for y and z, okay? You've just got to trust me on that one. So when we know that, we can define our boundary conditions, okay? And so we know that we have 0 conditions at this situation when kx is n pi over L. Okay, so L is the dimension of this cube, and pi is our frequency. Or not our frequency, is our distance. Yes.
I noticed x doesn't appear at all in our expression for kx, so would it be any different for ky or z?
No, absolutely. Yeah, so you could have this ky, and kz.
Is that just because it's a spherical behavior?
Because it's a three-dimensional behavior.
There's no bias toward any axis?
No, yeah.
That just makes me question, is the wave function, is that like psi of x? Because we use kx and x, or?
It's the frequency, the wave number kx times x at any given distance x.
Oh, okay, so distance from the center.
Yes. Okay. Where n is an integral. And again, sine of pi is 0. And so that's why that's a boundary solution. Okay? Okay. So if we were to think then of, I'm awful at drawing cubes, so let's have him draw the cubes. So at each of these points is a 0 frequency, right? Or there's a solution, there's a boundary condition, okay? So this is where you could think of one electron occupying a state. That's one solution to a wave function, okay? This is one state. Each of these cubes is a state, yeah.
The whole cube, like anywhere in its volume?
Yes, yep.
So
Because there's a solution at x, y, and z at the points on that cube.
So what about the boundary between cubes? Is that not zero?
Yeah, so that's like sine of pi. So here, like there, x is 0, there, x is 0, x is 0, 0, 0, 0, 0, 0.
But in between those little hash marks, it's not zero.
No, no,
Correct, it's not zero.
it is not 0. Yeah, yeah. I mean, yes, exactly. Okay, so then if we wanted to think about, so we know that n pi over L. So if we imagine our simplest cube where n equals 1, the distance for one of these cubes is pi over L. And therefore, the volume of one of those cubes is that. Okay? Now, what if we were to expand this out to a sphere, 1/8 of a sphere? Why 1/8 of a sphere? Because there, all of these frequencies are positive. Okay? That's why this is being drawn as 1/8 of a sphere. Okay? What's the volume of that sphere? Well, it's like it always is. It's volume equals 4/3 pi k cubed. And here we're assuming that the k, x, y, and z are isotropic. And so that we can just write k squared instead of kx times ky times kz. The volume of that is 1/8, right? Yeah, for the way it's drawn there. Okay? So if we were then to think about how many of these tiny cubes can I fit into this area, you just divide the volume of that 1/8 of a cube times the volume of one cube, right?
So we're saying like each of these little cubes is equal to one state.
One state.
And sorry, I was a little confused. Can you go over again how we like determine the volume of the state itself?
So you have boundaries where where this is 0. Where the k, where your solution to your wave function is 0. And that's what each of these lines represent, is where you have a boundary condition between states. Okay? Yeah?
What's the physical representation of the cubes? Is it just like atoms or what?
No, it's a range of frequencies that solve the Schrödinger equation. Right? Because what we're plotting here is different frequencies, right? So this represents, in 3 different dimensions, a range of frequencies that are a unique solution to the Schrödinger equation.
And that Schrödinger equation is for like a bulk silicon plate or whatever?
Well, no, that Schrödinger equation is for this one state that has been created by cramming all these atoms together. Okay? Yeah.
So why are you approximating it to a sphere instead of a cube? Like, in terms of the, like, you're saying it's 1/8 of a sphere, but they're cubed.
You certainly could have done that, but the classic derivation is to think of it as a cube. I bet there's a better answer, but I don't know it. Yeah.
Does it have to do with the fact that a cube is, or a sphere is something constant radius? So we'd expect something, even though its wave function would be uglier, something like out in the middle with x, y, and z.
Yeah, that could be it too.
Something purely x would be the same value, something purely y, or something up here.
Yeah, and you could think of like the contribution of a radial wave function. I don't know. Okay, so if we were to divide these two, then we would get. So now we're calculating here n, right? Number of the number of states, right? And so this is going to be 1/8 4/3 pi k cubed divided by that, right? So we're going to do L over pi cubed, okay? And there's one trick to throw in here that we need to multiply that by 2. Why? Spin up, spin down, right? We're calculating the number of electrons we could have in there, but each state, each cube could have a spin up or a spin down, okay?
Professor?
Yeah.
Is there a reason that we're only taking an eighth of the sphere, even though you said earlier it's possible, but since the sphere represents all possible things, couldn't, radially speaking, we talk about stuff that's over here, the negatives or something?
A negative frequency in the Schrodinger equation, I don't think people think about it that way, and that's why we always square the Schrodinger equation,
So
right, to
state-
think about the
so
probability.
this isn't directly super meaningful, this is more of a mathematical.
It's not, no, not at all. I mean, to think about this, that's why we really hammered on this, because to think about this as a physical dimension is wrong, right? What you're thinking about is a range of frequencies, not a distance. Yeah.
So if we have this cube that represents a range of frequencies, and then we Fourier transform it back into time space, where it's going
We're going to figure out a way to get rid of the frequency domain here. Yeah, we're going to eventually work this out so we're done with frequency domain, and we're not going to do a Fourier transform. Yeah.
Isn't negative frequency also unvisible?
Unvisible?
Or unphysical? Like
Non-physical. Probably. Yeah, I mean, what does a negative frequency mean? Yeah. I mean, yeah. It is an existential question, yeah.
We're ignoring the amplitude, right?
We are largely ignoring the amplitude unless that's incorporated into the B, the X up there. You do not have any axes for amplitude. That is right. And yeah. So I guess we are, but I'm not completely comfortable saying that. Yeah.
So the reason we have the equation in this form is because we already explained it too, we have the volume of the octave sphere, whatever,
Yep.
divided by the volume of an individual cube.
That's right. Yep. Volume of 1/8 of a cube. Volume 1/8 of a sphere over 1 cube. That's what this is.
So we're considering each of these as one state for n equals 1. Each of these little cubes.
Mm-hmm.
And so then, so k.
Well, you said for n equals 1. No, because like here, at this point, n equals 2 for kz, right? Right there. That's another solution. It's another place where z drops to 0.
So then how come we can set like the area of the entire sphere as equal to k?
Because we're just going to assume that these are isotropic, that these radiate out from the center of this imaginary place of 0 frequency equally.
So, but like, what I'm lost on is like why, like where the n term comes in for that,
Where the n term comes in.
the k cubed. So when you say like,
It doesn't. because here we're only looking at one cube, and so it could be for the n equals 1, right? All these cubes are going to have the same dimensions.
Right. So for the total sphere, it's like, what are we setting n equal to?
I mean 1, definitely. N equals 1 here. Because each cube is going to, let's just make it easy and have it be a cube of 1. Right? Yeah. Okay. So we can simplify this a little bit to pi k cubed over 3 L pi over pi squared. Okay. Now, this is how many electrons we can have in this situation, right? That's not what density of states is, right? Density of states is the number of states per unit energy, per volume.
Hey, Professor.
Yeah.
Why can't we take n equals 1 here and just drop the n from our k expression? The top one.
Why can we do that here? Because we're only looking at the volume of one sphere, or one cube, right? So if you here, like, okay, so what if you wanted to calculate the volume of this cube here? So you would do n equals 1, 2, 3, 4, 5, 6. So you would do n equals 6 minus n equals 5 equals 1 times, and you would look at the distance between that one cube, that one Robert, did you get that? Because you asked that same question. I guess it didn't fall through. He was like, why? He still wasn't satisfied with the n. And I said, okay, so what if you came over here and did n equals 6 minus n equals 5 equals 1, right? Or picked a cube up here. So it was 5 minus 4, and then, right? So you did the sides. Okay? Yeah.
But since they're all the same size, we just take 1.
Yeah, because it's just the volume of one cube. Yeah.
Can we just simplify this last equation into like pi over 3?
Yes, of course. Yeah. There's more simplification coming. We're just getting started. Yeah.
Why is there a number of states then? If you have like 2 counting for the spin numbers and not the number of electrons?
You could, thank you. Yep. Or what else could it be? The number of, who's what? Holes, I thought I heard it. It's the number, you could also think of this as the number of holes, right? Now, what if we tried to move this into the number of states per energy? So dN over dE, okay? So that's closer to what we want. So if we had this, and then we divided it by the volume, this would equal the density of states, right? Number of states per unit energy divided by energy. Okay? So the good news is we know the volume in this situation is 1 over L cubed. That's the volume. And so now we're to this, dN dE. Okay? Now, I hadn't thought about the chain rule in probably 15 years, but prepping for this lecture reminded me of the chain rule lovingly. And it turns out that we could rewrite this as dN dk dk dE. Right? Okay, so let's do something that's easy. dN dk, we have an expression here. So for n, so we can just take this. Sorry, I'm going to write it up here. So equals 3 pi k squared over 3. So our 3's cancel. We get rid of 1 pi. So we're left with k squared L squared over pi squared. Is that right? Yes. Pi cubed on the bottom.
No, it's squared because you cancel one.
Yeah, you cancel.
I canceled 1, that's squared. K squared pi squared. Yes. That's right. Okay. Sweet. So now let's put this over here, k squared L cubed. Okay, so sweet. We get rid of that term. Now, what do we do about this term, dk dE? This is where we have to get another little hand wavy because we just didn't have enough time to think more about particle in a box, but it turns out that there's this really well-established expression that relates energy, a change in energy to a change in frequency, and it's your Planck's constant squared, the frequency squared, over twice this effective mass. We'll talk about effective mass in a minute. Okay? So if we take this expression, we can, let me write it over here for room to tweak with this. We know 2 things. We know that k is the square root of 2me and over h bar. And we also know that dE dk is h bar squared k over m. Okay? And therefore, flip. Okay? So now we can plug this in for our expression here. M k h bar squared. Okay, good. We're getting rid of some k's. Km pi squared h bar squared. Okay? And then to get rid of this last k, we can use this, which is just rearranged from here. Square root of 2, square root of m, square root of e over h bar. And when you boil all that down, you get h pi. Oops. And you also see this written as, the trick here is h versus h bar. So when you start looking online, you'll see this written multiple different ways, and it took me a while. But remember that h bar equals h over 2 pi. That's an easy thing to miss. So if you pull this up online and you see it written as this, this is the same thing. And this is our density of states for a bulk system. Okay, so what does it depend on? Not a lot, right? Not a lot. It depends on the mass of an electron, which is, we'll see in a minute, it actually changes more than you'd think in these systems, and the energy, okay? Now, this should be kind of reminiscent, because when we first started making these generic diagrams, one of the ways we looked at it was to look at these density of states, and this kind of plot looks similar to the square relationship, right? So here in a bulk system, if we look at the density of states as a function of energy, for a bulk system, it has this square root of E relationship. Let's see, do I have it in another way? Yeah, like this one too. I like this one. Okay? Yes?
So energy is usually negative for these systems, correct? So is this the square root of the absolute value? Or the plus or minus the square root?
It has to be the absolute value. Yeah. As when the questions are generally written, it's so-and-so electron volts above the conduction band.
Okay.
Right? So you would think about it in that. So like what a question then could ask you is, if you had this kind of situation, what's the density of states? Let's just call this what's the density of states in that region? Right? Between 5 and 6 electron volts.
We just integrate the expression.
You can integrate the expression, yeah. Or there's, you can do it, you can make some more assumptions and it'll get even simpler. We'll do a homework on that. Okay? Now, while we're on, this is in your mind, let's jump right to a 2D system. Okay, let's keep this. This will come back and be important again. So what the hell does that even mean, a 2D system, right? I mean, you've probably seen this before, but I mean, can you believe that you can make this stuff so small that you physically can't move electrons in one dimension? I mean, that's what this is saying, is that frequency no longer exists in one of these dimensions, right? It's saying that you can move electrons in the x and y, or however this is written, but there's no frequency in one of those dimensions, right? That's what this is meaning. That's what this is saying. Similarly, in a 1D system, if you make like a nanowire so small, you can only propagate electrons in one dimension, right? That the size of the system impacts the frequency, right? Yeah.
So, like, outside of like a carbon nanotube or graphene, like, what would be examples?
Oh, like Don Serbely in our department makes these nanowires all the time that are 1D systems.
And like,
Yeah.
What sort of cross-sectional number of atoms are we talking about to calling 1D? What's the diameter of the atomic width?
You would think that it would be the de Broglie wavelength, right? That's what you would, I mean, if you just thought about it intuitively, it would be smaller than the de Broglie wavelength of an electron, which these systems are way bigger than that. And let me come back to that. It's a great point, but let me put that in another lecture. Because that's not true, right? Like quantum dots are clearly, up to 10 nanometers, which is way bigger than the de Broglie wavelength. Okay. So if we were to repeat this for a 2D system, now our life's getting a lot easier. We have just kx and ky, and the area is now pi over L, pi over L. Again, there's an n here, so we could come up here and draw this one. But again, this is still pi over L and pi over L. Okay? And so the number of states is 1/4 of the area of a circle. So number of E, I should be more precise with my language. This is indeed the number of electrons is 1/4 pi k squared over pi over L squared. Okay? Area of 1 cube, volume of this semicircle or 1/4 circle. Okay? So if we then rewrite this as dn dk pi k L over pi squared equals L squared k over pi. Okay, and now our same thing, density of states. We actually can keep a lot of this. We're going to change this, right? We're going to change volume to area. This will yeah.
When you take the derivative, should it be 1/2 pi k?
You start with 1/4.
You sure do, don't you? Yeah. I don't know how I missed that, but I guess.
Also, when we're calculating, because we're using like the number of electrons, shouldn't we use like the number of states? So
Oh, that's why, because there's 2. Yeah, that's why, because there's a 2 here. So you did have 1/2, and then you multiplied it by 2. Yep. Thank you. It all comes out in the wash. Okay, so now we're going to do 1 over A. And yes, what the hell did I have here? Yeah, 1 over A. And then chain rule again, dn dk. Okay, so the area here is 1 over L squared. And this we know is, when you simplify it down, right, this is dn dk. When you simplify this down, L squared k over pi. Yep, L squared k over pi. Sweet. And then dk we use again as m k over h bar squared. Okay, so we can get rid of this, and k's cancel, and we're left with m over pi h bar squared. Now, that's saying that there's no energy dependence in a 2D system. And that's what this is showing here, is that your density of states is independent of the energy. It's a constant. There's no frequency dependence or no energy dependence when we've shrunken it to that size. And, you know, of course, people have determined this experimentally many times. Yeah. At this line, that's when you go, that's essentially the band gap, right? That's where you're going from no states in the no states to states. Yeah. Yeah.
So what practical effect does this this have in practice? If there's no energy dependence, does that mean it's super conductive, or what are we talking about?
What does that mean? That means that it's a good question. Let me circle back to that. Yeah.
Would it just mean that the density is like homogeneous throughout the conductive bands? So there's not like a place of energy that is much more conductive? Or...
Yeah, it's that as these states are since there is a constant level, that it's not going to change as you start to use it across a variety of different energies, right? Which may be good or may be bad, right? So if we were to tease this out for, maybe that's a good homework, is to have you derive the expression for a 1D system. Now we come back and it's an inversely proportional to the square root of E, okay? Could you imagine like what that would look like? What would that look like if we were to do a 1D system? Well, you would just look at kx, right? So you would have pi over L, 2 pi over L, 3 pi over L, okay? So then you would do your total length over one state. Yeah?
It just reminds me of our previous question of why did the metal one look so different from the hydrogen density of states? And the hydrogen looks a whole lot like that 1D system because we were working with a 1D system.
Yes, thank you.
Right? So
yeah.
It makes sense that it would have looked like that it would have gone away from the center line.
Yes. So he was like, his point was that this looks very similar to what when we looked at hydrogen and linear hydrogen. Yeah.
I was wondering when you're deriving K over T, why exactly is K not energy, but derivative K turns to energy, doesn't have that energy?
Say it one more time.
So why for when you have the K constant right there, as it depends on energy, but then when you take the derivative, it turns to energy, there's no longer an energy constant, dk over dE.
There's no longer an energy constant. Yeah, because
K is included in that. It's K is going back. It's not taking any energy out. The energy is within K.
Oh, I see. So it's kind of like a larger.
because it's a frequency. Yep. So the relationship between these two becomes an energy, right? Yeah. The thing that I can't figure out, and if you guys will teach me, I would love it, is that I can't get the units to cancel here. That's joule second squared over second squared. But then there's that weird kilogram term there. I don't get it. I'm still working on it. But here's the answer to derive a 1D density of states. So it's, again, inversely proportional to, don't let that this is just a delta E. So maybe we'll have you try to derive it. I mean, you can obviously look it up online, but I think it would be a good exercise to walk through how you would do that. Okay, note that when we're talking about this, the mass in these situations is always an m star, and that means it's an effective mass. So that means, believe it or not, that how the mass of this electron, it changes as a function of being in this lattice because there's other forces on it. And so the mass of an electron in gold is different than in silver or copper. You would always be given that, but when you get to the homework, be aware that this is now an effective mass, okay? We'll see you on Monday.